Okay, everyone, we're going to now do some level 3 analysis, producing a linear graph including uncertainties. Now, so the key issue is we've decided the relationship is the square root of h. So we now need to transform our uncertainties from h to the square root of h. So to do that, here's our absolute uncertainty. We decided it was 5 mils or 0.005. Our percentage error, that's what we have to transform, is equal to, use a bracket because it doesn't know bed mass, this value here divided by the actual h value multiplied by 100. So that's our percentage error. It's 5%. Yeah, that's pretty easy to do. And we'll do the same thing for all of them. And you'd see that when we get down to 0.55 meters, it's only 0.9%. Now, I'm going to increase this to 2 decimal places, just so 2 significant figures, sorry, because that's the general practice. So we now need to transform that percentage error. Because it's square root, we're going to be using a half, because a square root is another way of expressing that as x to the power of a half. So it equals 0.5 multiplied by the percentage. So we're going to get 2.5%. So when you have h and its percentage error is 5%, the percentage error in the square root of h is half of that, which is 2.5. And it'll be the same for everything down there. So we take it down and you see we've now got some smaller values down here with less decimal places. So let's increase those a little bit. Now the absolute error is going to be this percentage of the square root h. So it's equal to, in this particular case, 2.5 divided by 0.32. Oh, sorry, that's incorrect. We've got 2.5, got to turn that into a percentage, which is divided by 100, sorry about that, multiplied by the h value, which is 0.32. So there's my percentage. There's my absolute uncertainty. I'm going to do that again because I muffed it up a bit. So our absolute uncertainty in the square root of h is equal to its percentage error divided by 100 to turn it back into a percent. Sorry, turn it back into a decimal, multiplied by the square root of h value. And obviously we can then just take those down and copy the formula because that's what spreadsheets are good for. Right, so there's our absolute error in the square root of h. Now we go all the way down to the time. Now I'm going to do 2 things. We decided that 0.2 is a good approximation for human reaction time, and that was our uncertainty in that timing. Is that a good approximation? Well, let's find out. This is called the range over 2 check. We're going to see how much the data is actually varying. So it equals, put it inside a bracket because it doesn't know bed mass, the maximum of my t values of that line, take away the minimum of my t values of that line, close a bracket because there's my range, and now divided by 2, the whole range, it equals 0.02. Not very much. So although we estimated it was at 0.2, in this particular case, it's only varying by 0.02 of a second. We drag all those down because it's the same thing each time. And you'll see that although there's one of them that has no variation whatsoever, there's one of them that has a 0.15 variation. And to one significant figure, 0.2 is a good estimate, so I'm going to leave it at that. Okay, so we're now going to work out the percentage error in t. So it's going to be equal, oh, what's going on here? Equal to the 0.2 out of your actual t value and multiplied by 100 to turn that into a percentage, gives you 13%. And we just drag that down. And so now, looking at the last one, say, here we have 0.2 is in fact of 0.53 is in fact 38%. Okay, so 38% is 0.2 divided by 0.53. Right, having worked out time, now we need to work out the percentage uncertainty in the length. So we were using a meter ruler. I was putting it on the 90 centimeter mark, so 0.9 meters. I judged that it was accurate to 0.9 0.01 to 1 centimeter each time. There's my uncertainty. I can drag all that down as a percentage error because we need the percentage errors because we've worked out V, and the speed is the length divided by the time, which means we have to add the percentage errors because we're doing a multiply or divide function. So I need this percentage error. So it equals, in brackets, that value out of that value, or multiplied by 100, 1.1%. And obviously it's going to be the same thing. There's the bell. It's obviously going to be the same thing each time because L is a constant. Now we can work out the percentage error in V because it's going to be equal to that value there and the uncertainty in T, that value there. So the first one is 14.5%. And we drag that down, and you'll see that the last one's, well, it's 1.1 plus 38%. And let's take all that down to only two significant figures. In fact, no, there's a reason for 3 because of rounding, so we'll leave it at that. And we work out our absolute uncertainty. Here we go, absolute uncertainty in V, which is equal to our 14.5, turn it back into a decimal. So we can use it to multiply value of V. So we're going to work out 14.5% of V, which is 0.087. And let's drag all that down to there. So we've now got all our uncertainty data. Let's copy all, let's Control A for the whole thing, copy all of that, and let's take it to our Plotly and pop it in here. Control V. Within, you can see there's all my headings. Let's put them all up on the toolbar. Right, so I want to add a trace. I'm going to default to scatter. I want square root of H on the horizontal and V on the vertical. Let's put them in now before we forget. V in meters per second. Oh, meters per second. And our time, not time, sorry, height. That's the square root of height. Right, to get the square root of height, I'm going to go in here and take that data and paste it in here because the square root sign will show up. There we go. Let's make that nice and big. Okay, now we need to do some, first of all, let's put our error bars on first. So that's under the style area, under traces. And if you scroll all the way down to the bottom, here we have error bars in X. I want them to be symmetric as opposed to not. I've got some data that gives that because it's not a single value. I go into here and there's my absolute error in H, square root of H, sorry. And then my Y value error bars, symmetric again. Got data for that. I scroll down and absolute error in V. Go. Let's go close that down now. Go to some analysis, curve fitting. I'm going to put a straight line on the lot. Okay, and I press run. Right, there we go. Let's have a quick look at this. Get it up high. Bring that down here. Let's get the origin on the screen. Okay, first thing I want to do is I want to take that y-intercept back to the origin. So advanced. Let's have our minimum. Let's go to negative 0.05 on the x-axis, and the biggest one can be 0.8. That's good to me. And run it again. There we go. Let's have a look here. Scroll that up, and you can see there's my y-intercept right there. That's not expected. We wouldn't expect a y-intercept, but that's what the uncertainties are for. So let's now very quickly put back to basic here, and let's just minimize this for the minute because I'm going to do another trace. There it is there, and turn it on. run it, and let's put it on advanced and send it back to 0 as well. And so negative 0.05, and I said it was to 0.8, I believe. Let's run that, and it obviously just appears exactly on top of it. You see it went darker. But here's the tricky one now. Let's go back to our basic window. We're going to lock these values, and we're going to play around with these sliders and changing the numbers to see what it could do. Now, I'm going right through the middle here. I'm going to try and bring the gradient down and bring the y-intercept up and see if I can still stay inside all the error bars. So I need a smaller gradient. Let's say 2.2. Let's run that. Oh, look at that. Okay, so there's my line of worst fit I'm mucking around with. You see it stays inside all those error bars, but it's gone out of sight of that one, and that's probably not justified. So let's increase this to negative 0.1, say. Run that. Okay. Now, you can see I've brought it back up inside that error bar again. Again, that one right there. I can take the gradient down a bit more. 2.0, let's try that. Run. Okay, that's looking good. Now you can see this is just going outside there. Okay, I think I could. But see, it's not just the bar on the bottom; it's the rectangle that's formed by these two bars. And I think that's just touching the edge. I think I'm gonna go with that. I don't think I want to bring that up any further. So I could bring it up to 0. What would that look like? No, see, that's no good at all. That's brought it up a ton. So negative 0.0, and then from 0.1, weren't we? No, I like that. I think that's about it. That's right on the edge there, and it's inside all the rest. So I think that's giving me my most extreme value I can still justify. So let's now open both of these up like so. Move the toolbar down so I can get my values both shown at the same time. There's my line of best fit and my line of worst fit right there. Yeah, I like that. Okay, I'm going to screen capture the whole lot. New. I'm going to take all this over here. That's what I'm after. Here we go. Let's copy it automatically. Let's go to my model answers. Scroll down a bit. Okay, paste your graph in here. There we go. Paste my graph in there. There's my graph. Okie dokie. Right. I've prepared beforehand because you don't need to watch me type. Right, so what we've got here is because we've got square root h against v. First thing, this means, as I say here, this means that v is indeed a function of the square root of h. Okay, so that's the shape of the pattern. We've confirmed that by getting a straight line. Okay, now let's look here. My y-intercept, so my gradients. This one is negative 2.46, and this one is exactly 2. So it's 2.0, but Polyglot for some reason doesn't like the 0.0 on the end. So those are my two gradients. I'm 2.46, I'm rounding up to 2.5. My y-intercepts, you can see negative 0.20 and negative 0.1. So those are my two values. So now let's think about this. The uncertainty in the gradient is obviously the difference between those two values, which is 0.5, and the uncertainty in the y-intercept is the difference between those values, and that's 0.1. So my equation, v equals the gradient, which with uncertainties is 2.5, my gradient, my line of best fit, plus or minus 0.5, multiplied by the square root of h, that's from the straight line. And then my y-intercept is negative 0.2 plus or minus 0.1. So that's it overall. And that will be the end of that.